In the last video, we left off talking about a situation where we would try to apply the comparison test, but we would fall into a scenario where we don't get a useful result. So we can generalize this where we have the assumption that a sub k is bounded above by b sub k. And with this relationship, the cases that were not going to be useful with comparison test was either the information that the sum of the a sub k's converges, or knowing that the sum of the b sub k's diverges. In either of these instances, the comparison test gives us no information. However, it's exactly in this situation that we can use what's called the limit comparison test. So I'm going to state this here, and then we'll look at some examples. So much like the comparison test, when we're using the limit comparison test, we're yet again assuming that we have two series with positive terms, or non-negative terms. Here, we don't really care if a sub k is greater than or equal to b sub k or vice versa. Instead, we're going to look at a limit. In particular, we're going to look at the limit of a sub k over b sub k. And let's call that limit c. If we find that that value of c is between 0 and infinity, so we want it to be a positive finite number, then we're going to be able to conclude that our two sums, that of a sub k and that of b sub k, either both converge or both diverge. Okay, a couple things to consider that when you're using the limit comparison test, notice that it is important that your limit not equal 0 or infinity. And we'll see that the reason is that we can have situations where that is the case, where the series don't in fact behave the same. But we can also have other situations where they do. So essentially, you can't conclude that they behave differently if the limit is 0 or infinity. It's really a case-by-case situation. So just to see this, let's consider a situation where that limit is equal to infinity. We could look at a similar example with 0. So one way that this could occur is if I'm comparing a sub k, which is 1 over k, and b sub k, which is 1 over k squared. In this instance, the limit of, let's say, a sub k over b sub k is the limit of 1 over k divided by 1 over k squared, which is the limit, if you simplify this, multiply by the reciprocal of k, and so we get infinity. In this instance, we ended up comparing two series that behave very differently. Here, the sum of the a sub k's diverges, right? That's the harmonic series. And the sum of b sub k converges. That's a p series with p equals 2, strictly greater than 1. However, we can look at a sub k equals 1 over k squared, b sub k equals 1 over k cubed. And we're going to see the same thing happens here. If I take the limit of a sub k over b sub k, which is the limit of 1 over k squared divided by 1 over k cubed, this too reduces to the limit of k, which is infinity. Here, both the sum of a sub k and the sum of b sub k converge. So the point of this example is to show that we have an instance where the limit is infinity, and we have that in this first example, the series behave differently. One converges and the other one diverges. In the second example, we have that the limit is infinity, but the series behave the same. They both converge. So this is pointing out that something different is happening here when the limit is infinity. I could do a similar idea with showing situations where the limit is 0. And what the limit comparison test is saying, if you were to take that limit and get any finite positive number, it would always be true that the two series behave the same. So basically, we want to avoid trying to use this where we have a comparison series so that that limit is infinity or 0. Okay, let's now look at examples where we start to use this. To begin with, I want to start with the example that I ended with in our comparison test video, and that was what led us to this situation where we had an inconclusive result for the comparison test. We were looking there at the sum from k equals 1 to infinity of k minus 1 over k squared. What I pointed out is that usually when you see a polynomial in k over a polynomial in k, the best comparison is to take the highest power in the top and the bottom. And in this situation, that would lead to the harmonic series. So we would have here that this is smaller than k over k squared, which is 1 over k. This we addressed in the last video. I'll point out, because this diverges, this is not useful in using the comparison test. Now, it's exactly these situations where you have something that looks almost like a p-series or almost like a geometric series where we said that comparison tests would be useful. It's exactly that situation that I want to jump to the limit comparison test. And the nice thing here is, notice that my statement of the test refers to two different series. If I tried the comparison test and it didn't give me the direction of the inequality I was looking for, then I moved to the limit comparison test, and those same two series I already tried to compare, those are going to be my a sub k and b sub k for the limit comparison test. So now I'm going to try what I'll call LCT, and now I take the terms of these two series and I consider the limit as k approaches infinity of one of those terms divided by the other. So this is the same thing as multiplying by k. So if I do that, I would have k squared minus k over k squared. Now you could use L'Hopital's rule, or notice that you have a degree 2 polynomial divided by a degree 2 polynomial. So the limit would result in the ratio of the leading coefficients, which would be 1 over 1 or just 1. So what this is telling me, if we come back to the statement of the limit comparison test, we just found our c value to be 1. Importantly, that certainly lies in between 0 and infinity. We didn't get 0, we didn't get positive infinity. That means that we can use the limit comparison test. And in particular, one thing we have to think about here when we're deciding the behavior of our series, it's not this number that you get that determines whether the series converges or diverges. That number tells me that I'm allowed to use this test. And in particular, if I had gotten 1 million here, that would mean the same thing as that 1 and telling me that I can use this test. The way that I decide whether or not the series converges or diverges is always by coming back to the information about my known series. The limit comparison test tells me these two series behave the same. So what I can reference now is that because I know that the sum of 1 over k diverges, and again, we know that because that's a p-series with p equals 1, then I can say that the other series, which has terms k minus 1 over k squared, that diverges. And that's because we know that they behave the same. And this is by the limit comparison test. So one question that I'm often asked when I teach this in person is about my arrangement of the top and the bottom and that limit there. So I took the terms of my original series and divided them by the terms of the series that I'm trying to compare it to. It does not matter if somebody else had flipped those and had 1 over k divided by k minus 1 over k squared. Importantly, if me arranging them in this way leads to a positive finite limit, somebody flipping them would also lead to a positive finite limit. So in this case, you would get 1 as well. But really, normally it would be the difference between, say, getting 10 and 1/10, getting 7 and 1/7. And because we only care about getting a limit that is positive and finite, that won't matter. So it really is arbitrary once you've decided on your two series as to which one you place in the numerator and which in the denominator. Okay, another example is the sum from k equals 1 to infinity of 1 over 2 to the k minus 1. So if I saw this series, I would notice that it almost looks like a p-series, right? Not a p-series, importantly a geometric series. And that's coming from what I'm circling right here. So my first instinct would be to compare this directly to 1 over 2 to the k, which we can see is 1/2 to the k. And now we want to think about the direction here. So the series that we're starting with has a smaller denominator, which means that it is overall larger than the one I have on the right. But we know that that series that I have on the right converges because the r value is less than 1 in absolute value. So this falls into the not useful situation in the comparison test. I've bounded my series below by a series that I know converges. So then I jump to limit comparison test, and again I use the same two series I have here. I'm going to take the limit of one of these terms divided by the other. Again, it does not matter which goes where. And I can write this as multiplying by instead 2 to the k. And this gives me 2 to the k over 2 to the k minus 1. This limit is the same as 1 over 1 minus 1 over 2 to the k. Now, to be clear, where did I get that? I can take the limit I have in the middle here and divide both the numerator and the denominator by 2 to the k. If I do that to the top and the bottom, I'm not changing the limit. And in doing so, it makes it easier to see what this limit approaches, because as k goes to infinity, this is going to go to 0. Consequently, this limit becomes 1. Now, it is a coincidence that I got 1 just like I did in the last example. Like I said, the only significance of that is that I got a positive finite number, which tells me that I can apply the limit comparison test, meaning that the two series I'm considering behave the same. So I can say that because the sum of 1/2 to the k converges, and then again, I want to justify why. That's because it's geometric, with the absolute value of r, which is 1/2, being strictly less than 1. Because that's true, I can say that the sum of 1 over 2 to the k minus 1 also converges. And I want to make sure that I reference the limit comparison test.